Four movements in this chapter: the problem and the model, why least squares fails for a binary outcome, and how the logistic curve repairs it, interpretation and estimation through odds and risks, a worked clinical application, and extensions with the generalized linear model supplement. The goals: explain why least squares fails for a 0-1 outcome, write down the logistic model, interpret coefficients through odds ratios, relative risk, and risk differences, understand maximum likelihood, and estimate average risk measures in both languages. Binary outcomes are everywhere: a heart attack or not, employed or not, voting for a party or not, buying a product or not. And here is the observation that organizes the whole chapter in the box on the right. When the outcome takes only the values 0 and 1, its conditional expectation is exactly the probability that it equals 1. Any model of a conditional mean is therefore a model of a probability. So what goes wrong with least squares? Three things: out-of-range predictions. A linear function of the regressor can exceed 1 or fall below 0, while probabilities cannot. Heteroscedasticity. The conditional variance is the probability times 1 minus the probability, which depends on the regressor, so the errors are necessarily heteroscedastic. And linearity. A conditional probability cannot be linear in a continuous regressor unless the model is saturated. The municipal data make the failure concrete. Regress an indicator for being in the top income quartile on the tertiary education share and read the fitted line. At a share of 20%, it predicts minus 0.12, a negative probability. At 60%, it predicts 1.23. Both are impossible, and a model producing nonsensical probabilities is unreliable for inference and useless for prediction. The fix is to pass the linear index through a function that is bounded between 0 and 1. Cumulative distribution functions do exactly that by construction. Two are conventional: the standard normal, giving the probit model, and the logistic, giving logit, or logistic regression. Both produce very similar predictions, and logit is more common because its coefficients carry a clean odds ratio reading. The logistic function itself, the exponential of the index over 1 plus that exponential. It always lies strictly between 0 and 1. It is symmetric, so the value at minus theta is 1 minus the value at theta. It is S-shaped, flat near the extremes and steep in the middle, and it passes through 1/2 at 0, approaching 1 and 0 at the two limits. Substitute the linear index into that function, and we have logistic regression. Three consequences to note. The sign of a coefficient gives the direction. Positive means higher regressor values raise the probability. The magnitude cannot be read directly and needs a further transformation. The parameters cannot be estimated by least squares. We use maximum likelihood. And the fitted curve is an S shape trapped between 0 and 1. With several regressors, the model extends in the obvious way, and the key line is the second. Holding other variables constant, a 1-unit increase in a regressor changes the log odds by its coefficient. Written the other way round, the log odds of the outcome, the logit, is linear in the regressors. Logistic regression is a linear model, but on the log odds scale, not the probability scale.